do that. So if you nailed a couple of them on the first one, nail them again, then they won't be on your thing on Friday. So you'll only get the stuff that you need to do. The other thing is you don't have to do everything, obviously, right? This time it may not be so bad, but as we keep going, it might be the case that there's more things in your stack than you could possibly do in an hour. That's okay. Nail what you can nail and leave the rest for the next time, okay? The last thing is, what section does it go up to? Any guesses? Oh, okay. Well, we're about to do 1.5, which is on continuity. That will be the first thing that's not on it. Okay, so it'll go up to what we did Friday last week, which is 1.4, the one-sided limit stuff. Okay, right. And then 1.5 will be the first thing for the next one, and so on, right, as we keep going. I kind of like to have a little bit of a lag between when we do something and when I expect you guys to be ready to do an exam on it. Partly because, well, you need time to do homework and study and that sort of thing, right? So, yeah. Okay, so let's talk about continuity. And let's just go straight for the kill. So let me just draw a picture of something that's not continuous. And I'm just going to pick something sort of random like this. Okay, so from a high school standpoint, this thing is clearly not continuous. Why? What was the high school definition of continuity? Yeah, I can draw it without picking up our pencil. Okay, which honestly is not that bad of a definition if we carefully encode what we mean by without picking up your pencil. Okay, so the reason that this thing is continuous, let me draw another example where it is continuous. Okay, something like, oops, go away, Siri. Well, let me call this one G of A. Okay, so here G is continuous, and yeah, I had to pick up my pencil, but only because I wanted to draw the dot, right, to make it sort of obvious. Okay, so in the language of limits, what we want to encode is why is the second one continuous and the first one isn't? Okay, so what's maybe a way to express that? Like, what's going on limit-wise with that first one? Yeah, there's a jump discontinuity. Okay, now but in terms of limits, what's going on with the limit as x approaches a of f? Yeah, it doesn't exist. And why doesn't it exist? Okay, so the left and the right hand limits are not the same. But if I came up with an example like this, now they are. The left and the right hand limits are. Oh, that's not what I meant to draw. Sorry, just a moment. There, how about that? Okay, left and the right hand limits are the same now. Gotcha. Except what's the problem then? So the limit exists, and it's whatever the y value of that hole is, but we would still say this thing is discontinuous because why? Yeah, there's a break in the line, and even if I didn't draw the dot that's up there, we'd still say it's discontinuous. Okay, how could I make this thing continuous by changing one point? Just one single point. Yeah, fill in the hole. Like, so if I move that dot and stick it into the hole, then we're set, right? And you guys would agree that in that circumstance, it would be continuous. Okay, so good. That brings us, therefore, to the definition of continuity, the college definition, I should say. Okay, so keep these pictures in mind. Let me flip to the next page. Is that okay? Because I need more space. Yeah? Okay. So, f of x is continuous at x equals a means okay, so three things have to happen. Now, strictly speaking, we could have just made the third thing the definition only, but it's maybe a little bit better to include the first two. So the function has to be defined at the point that you're interested in. Okay, that means that there has to be a dot somewhere. The second one says that if there's a hole, the function approaches the same, like there's only one hole, not two. Okay. And the third thing says the dot has to be in the hole, basically. Okay. Now, the second thing, this business about the limit, under what circumstances does that limit exist? Like, what's required for a limit to exist? What do you have to check, possibly? Yeah, you got to check from the left and from the right, and you might have to do that separately because, well, who knows, right? So, right, so we could break number two there into like 2A and 2B or something. But yeah, there's the definition, okay? And notice that we haven't said anything about picking up pencils, right? So it's a more precise definition. Okay. Now, uh, the other thing about this definition is that notice that I've defined it at a point A, so specific X number. Is it possible to be continuous at one place but not in another? Yeah, totally. And we could draw all kinds of squiggles up on the board where, and a lot of the graphs that we looked at last week, right, were continuous at some points, but not at all of them. Okay, so continuity is a what we call a local property because it happens, you can be continuous at one point, but not necessarily another. Okay, all right, now that said, if you can be continuous at one point, maybe you're continuous at a whole bunch of points. Okay, and so if that we say f of x is continuous on a set or an interval I if for every a in I, f is continuous at a. Okay, so let me just make sure. That symbol, you guys seen that before? Right, so what does that mean? Not quite. It's not all real numbers either. That's a different symbol, yeah. Yeah, it's in, so for every a in I. So that symbol is set membership. Okay, so a thing, an item is inside the set. We would write that little, looks like the Greek letter epsilon. Okay, now the for every symbol that Owen mentioned is an upside down A. Excellent. Okay. Yeah, well, there'll be a quiz. Yeah. Um, yeah, okay. Um, yeah, so that's just set theory notation. And yeah, is anybody else besides Owen going to do CS or interested in doing CS? Yeah, you'll get there, right? Just wait. Um, okay, so yeah, you can be continuous at a whole bunch of places, uh, and yeah. Now, there's one other thing. So let's think about functions that we know. Functions that you know that are continuous. So just start throwing some functions out there. Okay. Polynomials. Okay, check. Logs, when they're defined. Exponentials. A constant, yeah, we could put that in polynomial, but we'll list it separate. Okay, what else? Sine and cosine. But not tangent in the others. Okay, they all have asymptotes. So just sine and cosine from the trig functions. Anybody else? Square roots, when defined, absolute value. Another one we'll talk about, let's say, rational functions when defined. Okay, what is a rational function? Is it like a function that sits around and thinks very deeply about life and the universe? Yeah. It's a fraction of what? Not just any old fraction. The top and the bottom have to be a specific kind of thing. That's okay. We'd call that a rational trigonometric function because it's got trigs in it. Yeah, a rational function by itself, though, the top and the bottom have to be polynomials. Okay, that could be constants. Okay, so like 1 over x is rational. 1 over cos x is, well, not rational unless you include the trig functions. Yeah, that's just the rule. So what's the issue with rational functions? Well, if you get a function in the denominator, what might happen? Yeah, you could have a division by 0, right? That can happen. And when is the denominator 0? Well, if it's a polynomial, you have to figure out what the zeros of that polynomial are, which can actually be a bit of work, as you guys maybe remember from high school. Do you guys remember doing like Descartes' rule of signs or the rational root theorem or polynomial long division or synthetic division? Is this ringing any bells? Yeah, so finding roots of polynomials can be quite the bear. Just is. But yeah, so rational functions can be kind of tricky because of the algebra, not really because of the calculus. Okay. Okay, so now there's a lot of reasons why continuity matters, and we'll talk about one consequence of continuity here in a minute. Now, let me see if I can get the dang projector to work correctly this morning. I hope it's not my dongle that's gone bad. That will make me a very sad panda. Okay, forget it. We'll just do it on the iPad. How about that? Okay, so we'll try this. Let's do Wolfram Alpha. Okay, so the function I want to define is e to the minus x minus x. Okay, so I'll just use the Wolfram Alpha app and let it do its thing. It's not as good as Mathematica, but c'est la vie. And eventually it'll get connected and it's going to be one of those kind of Mondays I can smell already. You know, that's kind of what I'm wondering is if there's an issue with the Wi-Fi. I mean, I'm certainly connected, but let's try a web page. Great. Okay, well, all right. Let me just improvise and do this the old-fashioned way. So let me draw a picture. And it's kind of a silly picture. Okay, so let's say that we have y values there between 0 and 1. Just going to make up some numbers, who cares? Okay, if the function's continuous, pick a number between 0 and 1. 0.69, of course. Thanks, bro. Okay. You know we're live on the internet. Well, maybe not, because the stream may be down. So, right. How about for the sake of the children, let's do 0.7. That one, the back there. All right, so 0.7, right? You just picked some random value between 0 and 1. Is there a point that the function achieves the value 0.7? Okay, and from the graph, it's obvious that there is. Okay, and where is it? Well, it'd probably be somewhere over here. Okay, roughly. Now, how did I know that that was going to happen? I mean, the graph sort of gives it away, right? But how I knew it was going to happen is because I have a continuous function. So a function that's continuous, if it's one value at one point and a different value at a different point, then somewhere in between, it achieves all the values somewhere in between. Okay, now, does that seem like it's so obvious it shouldn't be anything fancy to say? Well, congratulations, then, you're a physicist. Okay, so let's write out the stuffy theorem and then kind of work through what it means. Okay, so theorem. This is called the intermediate value theorem. Okay, so suppose f is continuous on some interval ab, and that f of a is different than f of b. Okay, so that just means that at both ends of the interval, the function has two different y values. Okay. If c, well, let me say it this way. If d Okay, so that happens. So if you have a function that's continuous, it achieves all values between what it does at one end and what it does at the other. Okay, and I'm sorry if my handwriting's a little terrible. There exists a C. Yeah, sorry. If D, so let me fix that, make it look a little bit more legible. Sure. Look at something and say it's just like a text entry, like f of b plus x equals like a number. Like, could you say that there is an actual value if you only have something that goes from A to B? You don't know if it goes above C or there. Right. Okay. You can't use the theorem then, right? So it only applies between the two extreme values. Now, if you change the interval, you might be able to, because your interval might get you more values. But what this, yeah, you can only guarantee it for values that are in between f of a and f of b. Okay, so a good example of that would be like, think of the sine function, right? Is there ever a point where sine equals 2? No, right? And if you tried to misapply the theorem, you might think that there is such a point. Yeah, question? D is something you pick, f of a and f of b. Okay, so D is a y value, not an x value, right? And what I'm saying is, all right, you pick a D, a y value that's between f of a and f of b. Is there a C so that when you plug C into the function, you get D? And I claim that yes, in fact, there always is. Okay, yeah. Now, here's the thing that drives you guys, or drives, I think, a lot of people crazy about this theorem. Does it tell you where C is? With one exception. It's somewhere in between A and B. Other than that, you have no idea where C is. In fact, there could be 15 values that make this work. There could just be one. That depends on the function. So this is a theorem that we mathematicians call an existence theorem. There is a thing. You want to find that thing? Hey, that's your problem, man. Right? Finding the actual value C is another, like if for a specific function, that's more of an algebra problem. Okay, but we know that there's one there to be found. Okay, so that may seem a little silly, but maybe think of it this way. Let's say you want to dig up some diamonds. Okay, where would you go if you wanted to go digging for diamonds? Huh? What? Y level 13? Oh, yeah, okay, sorry. Yeah, okay. I thought you said Y level 13. I'm like, what? Okay, yeah, all right, fine. All right, so that just shows you how much Minecraft I've played. And in fact, uh, I've deliberately avoided getting into Minecraft because I know what would happen if I did. Uh, that sounds pretty accurate, yeah. But the point is that there would be the addiction phase where I would like, well, it's kind of like if you guys seen the World of Warcraft episode of South Park, when they're all like down in the basement and they're all like fat and pimple covered, and there's the guy with like the Cheetos and stuff, right? Um, yeah, I'd end up like that playing Minecraft, and as much fun as that sounds, I do have a job to do, right? Um, huh? Just yeah, McKinney's playing binging Minecraft this week, so no calculus. Yeah, but see, that's the thing. There's too many of you guys. And if there's anything to learn about criminal enterprises, is that somebody always talks. And, since I can't make you guys sleep with the fishes, uh, well, I guess I could, but that seems like a little extreme for just playing Minecraft for a few days. Right? Um, no, so the key, gentlemen, is to find a way that work can be play, like, oh, I don't know, teaching a game design class. And then you could be like, we're doing research. Yeah. So, okay. But yeah, so joking aside, right? Where would you dig to find diamonds? Oh, yeah, okay. Not straight down. That's a long way, bro. Yeah. So, that's maybe a silly way, but like if I hand you a shovel and send you out into the lawn to the mall, are you likely to find a diamond? No. All right, what about if I send you to the Diamond Crater State Park in Arkansas and hand you a shovel? You're much more likely to find something, right? So if this is an existence theorem in the sense that it points you in a direction. There's a diamond, or what is it? There's gold in them there hills, right? This is a there's gold in them there hills kind of theorem. Yeah, I reckon. Yeah, my Southern heritage is coming out here a little bit, but yeah, okay. So it's an existence theorem. You want to find the value of C. That's an algebra problem, okay, and sometimes a really hard one at that. Okay, so give you let's do kind of an example of how we could apply this theorem to a sort of realistic um, case or something not so cheesy. So let's take this polynomial equation. Okay, so I've got an equation here. Okay, and this is a kind of equation we might want to solve for some reason. I don't know. But it's an x to the fifth thing. Those are kind of hard to deal with, right? In particular, do you guys know a formula for fifth degree polynomials? Like you know the quadratic formula for quadratic ones, right? Do you guys happen to know the cubic formula? No, you don't. But it's worse. Like so, okay. So what's the song that goes with the quadratic formula? Did you guys learn this? You forgot it? Pop Goes the Weasel. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Right? Did you guys not learn that? You just compartmentalized it, and you have weekly sessions with Jamie Douglas to talk about the trauma of high school algebra. No? Okay. So yes, Mrs. Gurley. Did I tell you guys about Mrs. Gurley? Yeah, my algebra teacher. Yeah, she made us sing that, and it stuck with me. And it's been useful as a teacher. But if that's the song that goes with the quadratic formula, then Anagata Davida is the song that goes with the cubic formula. Okay, do you guys know that song? Dun dun da 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 dun 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 da da dun. No, not ringing any bells. Okay, well when the Wi-Fi gets back up, we'll play it. How about that? It's like 30 minutes long. So it turns out that there is you guys know the quadratic formula. There is a cubic formula. It's just really nasty. There is a fourth degree formula, which is even more nasty, but there is no fifth degree formula. And we even can prove that there can never be one. Like, is that like, no? Like, what is it about 4 and 5? Oh, well, yeah. This is the point where you do that. You guys know the meme with like the exploding brain that, like, yeah. I really should do a freshman tutorial on memes. I think that'd be a lot of fun. So, okay. All right. So, on this interval, does this thing have a root? Now, finding that root is another problem. But to return to our cheesy gold or diamonds or whatever, right? You'd like to know that there's gold in them there hills before you start digging for said gold, right? That's what the intermediate value theorem tells you, is that there is gold to be found. Okay, so how could I approach this? Well, first off, do I have a function? Yes and no. Right, what do I really have right now? Got an equation. How can I turn that into a function? Well, there's two ways I could approach this. One would be, and this is a common technique, let's just put everything on one side and then call this part f of x. So we're looking for when f of x is 0. Okay, that's not a problem. Okay, so I've got this interval here. What is f of 0 and what is f of 2? F of 0 is minus 3. Okay, that one's easy. What's f of 2? Now, a little bit more arithmetic, but I'll let you guys crunch it out. Because if there's anything to know about mathematicians, we are terrible with arithmetic. That's why we're mathematicians and not accountants. 77. What's the peanut gallery say? All right, good enough for me. All right, so how do I then apply the intermediate value theorem? I've got two numbers, -3 and 77. What's in between there? A whole bunch of stuff, right? And which one's the one that we care about at the moment that's between them? I mean, like 17 is between them. Great. Do I really care about 17 right now? Value, huh? Okay, why 1? So here's what's the y value we're interested in achieving? 0, okay. Is 0 between these two numbers? Yeah, last time I checked. Okay, so since -3 is less than 0 is less than 77, by the IVT, intermediate value theorem, okay, there exists C with, well, actually it's strict less than, sorry. Okay, there's a root to be found. Now, how you find that root, or techniques that you can use to find or approximate that root, is another matter. Okay, and in fact, one of the things that we'll talk about later on in the semester is a calculus method to approximate the roots of these things. It won't necessarily give you the exact answer, but it'll at least kind of get as close as you want, right? So you tell me that you want to be no more off than this number, I can work through an algorithm a number of times to get it that good. Okay, all right. So maybe another example here would be, I like this one. All right, so let's suppose that you've got a monk and he's in Tibet and there's a monastery up on the top of a mountain. And so one day he decides, you know what, I'm going to go visit that monastery. So at 8 in the morning, he starts walking up to the monastery and he gets there at 8 at night and he goes to bed. Then the next day he says, yeah, that was pretty nice visiting that monastery. Time to go back. So at 8 in the morning, he leaves the monastery, climbing back down the mountain. And at 8 p.m., he lands right where he started. Okay? Perfectly good situation. Yeah? All right. Is there a time at which, so let's say that the monastery, like he starts at ground level 0 and that the monastery is at ground level 1, just whatever. Okay, so halfway through the voyage, where is he y value wise? Probably. Yeah, somewhere in the middle, probably. Okay, but maybe it's not exactly in the middle. Like maybe he's a little further because he goes faster in the first half and then he's tired and slows down a little bit. Okay, but he's somewhere in the middle, right? Is there a time when he's at the same height at the same time on both days? Yeah. So this would be like at 3 p.m., he is at y value 0.6 both directions, both going up and coming down. Do you think there is such a point? No, because at 8 a.m., where is he on the second day? He's at the top, not at the bottom. And it's flip-flop the other way, right? So at 8 a.m. on the first day, where is he? He's at the bottom. At 8 a.m. on the second day, he's at the top. At 8 p.m., where is he on both days? Other way, okay? Well, let's draw a picture to kind of think about what's going on. So if we say there's a 12-hour period, okay, and what we're saying is on the first day, his curve looks something like this. And on the second day, it would look something like this. Is there a point where those two curves intersect? Okay, there is because I've drawn a picture, but maybe that's not exactly how he climbed up and down the mountain. Maybe the squiggles look different. Can you guarantee that there is such an intersection point? Yeah. I claim that you can guarantee there is such a point. Now, I can't tell you where it is. I can just say that it exists. It's just kind of like, right? No? All right, so let's do a trick. All right, so let's let, oops. Damn it. All right, so let's let f of x describe the climb up and g of x describe the climb down. Perfectly good, right? First off, is it reasonable to say that these are continuous functions? Under what circumstances would the functions not be continuous? Continuous. He'd have to have a teleporter, basically. Right? So we can assume that this is a continuous walk. Even if he stops for a little while, it's still continuous because the curve would look sort of like that or something, right? That's continuous. Maybe it isn't all that smooth looking, but it is continuous. Okay, so the first thing I want you to answer are what are these four values? Oops. Okay, so here I'm using time 0 to be when he starts and time 12 to be when he arrives. Okay, so what are those four values? What are the f values? Where does he start? At height 0. Where does he finish? 12 hours, but what's the height? 1, right? And I just made it 1, right? Because we could scale units, and maybe it's 10,000 meters. I don't know, right? All right. What about with g? What's happening there? Yeah, it flips. It's the other way. 1 and then 0. Okay. So sneaky mathematician trick. Oops. I'm going to consider the difference of those two functions. I'm going to call that new function h. Okay, and the reason I'm going to do that is because the intermediate value theorem applies to one function, not two. And so I need some sort of way to take the two functions I've got and put them together to a single function. Okay, now I could have done a whole lot of other ways to combine f and g. I could have added them, I could have multiplied them, I could have composed them, right? going to do all kinds of crap. I choose to do the difference because I know it's going to do what I want. Okay, so this is the mathematician trick, right? Okay, what is h of 0? And what is h of 1? Okay, so what are those two values? And I claim that it's pretty easy to compute them, given what I've told you. Okay, agreement? Yes. Okay, how'd you get that? Well, what is h of x? It's defined to be f of x minus g of x. So we just have to subtract the two values. Okay, so we get -1 at one end and 1 at the other. Okay, so what does the intermediate value theorem say? Therefore, is 0 in between -1 and 1? Last time I checked. Okay, so the intermediate value theorem therefore guarantees there's a time so that h of c is 0. Yes? Well, what was h of c? Or hold on, let me make sure that's clear. Agreement? Disagreement? We? No? Okay. Well, what was h of x? H was the difference of the two functions, right? And so if h is 0, if their difference is 0, then what has to be true about them? They're the same thing. So there's a time when he's at the same height, both the trip up the mountain and the trip down the mountain. Wow. Is that kind of mystifying? Do you believe me or think I'm still full of shit? Huh? Stupidly, it makes sense. Okay, now, fair point to that statement. Okay, that stupidly it makes sense. If Dr. Brown were out in the hallway right now and heard what we were saying, this is one of those points where he would make fun of us as mathematicians. He'd be like, this is obvious, but you guys have to make theorems and crap out of it and make a mountain out of a molehill that anybody with a half a brain would tell you this is true, right? And to some extent he's right, but you know, that's the business of mathematics, is being really careful. Because that occasionally happens with the physicists. They just do shit and then they leave us to clean up the mathematical mess, so to speak. Anyway, plus it's an opportunity to give Dr. Brown crap, because believe me, he'll give it right back. So, okay, so that's continuity. I'm sorry the computers are being so ornery today with Wi-Fi and the display thing. I don't know what the problem is there. Yeah, so we'll carry on Wednesday. Thanks for coming. Thanks for playing. And just quick reminder, right, that Friday is our next in-class assessment. And you guys are certainly welcome to schedule retakes avec moi in the office, 2 per week, 2 standards per week. Okay, Gucci. And if you want to schedule something, just send me an email. Give me, the more notice, the better. But it doesn't have to be like an exact number. Just send me an email and we'll figure it out. All right. See you guys later.